Chapter 8.2 Transformations of Logarithmic Functions. Recall the effects of parameters a, b, h, and k on any graph y equals f of x. A is our vertical stretch, b is our horizontal stretch, h is horizontal translation, and k is the vertical translation. Example, sketch the graph of y equals log x. Remember that is log base 10 of x since there is no base number written. Using your knowledge of transformations, sketch y equals log base 10 of x plus 4 plus 2. So let's start by graphing log base 10 of x. I often have trouble thinking about the graph of a log function, so I will graph an exponential function and then graph its inverse. So I'm going to look at y equals 10 to the power of x, the exponential function up here. When x is -1, y is 1 over 10. When x is 0, y is 1, 10 to the power of 0 is 1. And when x is 1, 10 to the power of 1 is 10. The inverse of that function is y equals log base 10 of x. So I can switch the x and y values from y equals 10 to the power of x to get the x and y values for log base 10 of x. 1 over 10 and -1, 1 and 0, 10 and 1. Now I can graph y equals log base 10 of x. When x is 1/10, so really close to 0, but just on the positive side, y is -1. When x is 1, y is 0. And when x is 10, y is 1. Join those points together. And there's our graph of y equals log base 10 of x. Next, we want to apply these transformations listed here. Y equals log base 10 of x plus 4 plus 2. So this here means that h equals -4. And here k equals 2. So that is a horizontal translation left 4 and a vertical translation up 2. So I take my points and shift them left 4 and up 2, starting with 1 over 10 and -1. 1, 2, 3, 4 to the left and up 2, so about here. The point 1, 0 goes 4 to the left and up 2, so it's now at -3, 2. And the point at 10, 1 goes 4 to the left, so it's at 6, and then it goes up 2, so it's at 3. Join those points together. And that gives us the graph of y equals log x plus 4 plus 2. Part A, what is the equation of any asymptotes? This would be for the transformed graph. So we have a vertical asymptote at x equals -4. So our vertical asymptote of log base 10 of x is at 0. It's been shifted 4 units to the left since h is -4. So it would be at x equals -4. State the domain and range of the transformed function. Well, we saw that our vertical asymptote's at x equals -4, and all our values are to the right of that. So our domain would be x such that x is greater than -4 XER. And our range, this function still goes forever down and forever up. So YER is our range. What are the x and y intercepts? We can do this algebraically by subbing in 0 for the appropriate variable. Starting with the x-intercept, set y equal to 0, we get 0 equals log x plus 4 plus 2. We want to isolate the x, so subtract 2, we get -2 equals log x plus 4. We need to separate the x and the 4, but they're both in a log. We haven't learned how to separate those yet, so we need to change it to exponential form. The base, remember, since there is no base written, it's 10. So 10 to the power of the exponent, which is -2, equals the argument, x plus 4. Then we subtract 4 to get 10 to the -2 minus 4 equals x. And we can calculate that. 10 to the power of -2 and then minus 4, which is -3.99. That's our x-intercept. Then for the y-intercept, do that up here. Sub in 0 for x, so y equals log 0 plus 4 plus 2, which gives us y equals log of 4 plus 2, which we then calculate. Log of 4, move out of the log, plus 2 is 2.602. We'll just put 2.60. So y-intercept is approximately 2.60. Sketch the graph of y equals -2 log base 5 of x plus 5 plus 4. So again, I have trouble thinking about graphs in terms of logs. So I'm going to think about the inverse function, the exponential function y equals 5 to the power of x. And I'm going to write some points down for that. So when x is -1, y would be 1 over 5. When x is 0, 5 to the power of 0 is 1. And when x is 1, 5 to the power of 1 is 5. Then for the inverse function, y equals log base 5 of x, we switch our x and y values. So 1 over 5, -1, 1, 0, 5, 1. Then I can plot those points to begin with. X is 1 over 5, y is -1. X is 1, y is 0, and x is 5, y is 1. Join those points together. And there's our graph of log base 5 of x. Now we can apply our transformations to get the graph that we're actually trying to get. So in terms of transformations, we have an a value of -2, which is a vertical stretch factor of 2, and reflection across the x-axis. Then we have a h value of -5, which is a horizontal translation, 5 units left. And we have a k value of 4, which is a vertical translation 4 units up. So we can use mapping notation. A point x, y on y equals log base 5 of x would be mapped to a point x minus 5, negative 2y plus 4 on the transformed function. Let's do that for each of the 3 points that we have in our table. 1 over 5, negative 1, 1 over 5 minus 5, and negative 2 times negative 1 plus 4. 1 over 5 minus 5 gives us negative 4.8. And negative 2 times negative 1 is 2, plus 4 is 6. Then our next point is 1, 0. One minus 5, and negative 2 times 0 plus 4. That gives us negative 4 and 4. And then 5, 1 is mapped to 5 minus 5, negative 2 times 1 plus 4, which is 0, and a negative 2 plus 4, which is 2. Plot those points, negative 4.8 and positive 6, about here, negative 4, 4, and 0, 2. Our vertical asymptote, which was at x equals 0, would have been shifted according to h, so 5 units left. So that would be at negative 5. Join our points together. And there is our graph of y equals negative 2 log base 5 x plus 5 plus 4. What is the equation of any asymptotes? We already saw that. There is a vertical asymptote at x equals negative 5. State the domain and range. Since we have a vertical asymptote at x equals negative 5 and all values are to the right of that, then our domain is x such that x is greater than negative 5, xer. And the range, same with y equals log base 5x. The range is y such that y is an element of the real numbers. And then what are the x and y intercepts? One of our points was the y-intercept. So y-intercept at 2. The x-intercept we can do algebraically or graphically. I'm going to start up here. Sub in 0 for y, we get 0 equals negative 2 log base 5 x plus 5 plus 4. We want to isolate x, so subtract 4. Negative 4 equals negative 2 log base 5 of x plus 5. Divide both sides by negative 2, we get positive 2 equals log base 5 of x plus 5. We want to separate the x and the 5, but they're both in the same log, so we need to change to exponential form. The base 5 to the power of the exponent 2 equals x plus 5. Then subtract 5. We have 25 minus 5, which is 20, equals x. So our x-intercept is 20, or the point 20, 0. And we didn't draw our vertical asymptote for the first graph, so let's do that. It was at -4. Sketch the graph of y equals 3 log base 2 of -2x plus 6. So I want to start by sketching the base function y equals log base 2 of x. To do that, I can think of the inverse of that, which is the exponential function y equals 2 to the power of x. We've sketched this one many times. When x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. So switch the x and y values to get the points for y equals log base 2 of x. (1/2) -1, 1, 0, 2, 1, 4, 2, and 8, 3. Plot those points. 1/2 -1, 1, 0, 2, 1, 4, 2, and 8, 3. Join those points together. And there's the graph of y equals log base 2 of x. Now we can look at the transformations. So looking at our function, y equals 3 log base 2 of -2x plus 6. Notice that this is not factored. We need to factor that. Then we get y equals 3 log base 2 of -2x minus 3. So our transformations, we have a equals 3, which is a vertical stretch factor of 3. B is -2, which is a horizontal stretch factor of 1/2. And reflection across the y-axis. And then we have h is 3, so a horizontal translation, 3 right. Our vertical asymptote is affected by the h value, so it's going to be shifted 3 to the right. So I can draw that. And that answers part A, the equation of any asymptotes. We have a vertical asymptote at x equals 3. Now let's use mapping notation to figure out what these points become on the transformed function. I'm going to do that up here. We have x, y is going to be mapped to -1/2 x plus 3 and 3y. So the point 1/2 -1 is -1/2 times 1/2 plus 3, and then 3 times -1. -1/2 times 1/2 plus 3 gives us 2.75. And the y value is 3 times -1, so -3. Next point is 1, 0. -1/2 times 1 plus 3, and 3 times 0. That gives us -1/2 plus 3, which is 2.5, and 3 times 0 is 0. Next point is 2, 1. 2, 1 is mapped to -1/2 times 2 plus 3, and 3 times 1. That gives us -1 plus 3, which is 2, and 3 times 1, which is 3. Next point is 4, 2, which is mapped to -1/2 times 4 plus 3, and 3 times 2. -1/2 times 4 is -2, plus 3 is 1, and 3 times 2 is 6. And last point is 8, 3, which is mapped to -1/2 times 8 plus 3, and 3 times 3. That gives us -4 plus 3, which is -1, 3 times 3, which is 9. Now we can plot these points. First one is 2.75 and -3, 2.75 and -3 is about here. Then we have 2.5 and 0. 2.5 and 0 is about there. Then we have 2, 3, 2, 3. Then we have 1, 6, 1, 6. And then we have -1, 9, -1, 9. Join these points together. And there's our transformed graph. Y equals 3 log base 2 of -2x plus 6. State the domain and range. The domain of the transformed function. We know that the vertical asymptote is at 3, and we see that the graph is on the left of that. So x such that x is less than 3, XER. And the range is all real values, so y such that YER. Then the x and y intercepts. We already had the x-intercept. It was one of our points right here, 2.50. And we can algebraically solve for the y-intercept. I'll start it up here. Y equals 3 log base 2 of -2 times 0 plus 6. Y equals 3 log base 2 of 6. And then calculate. 3, then I want log where I can choose my base. So down here, base is 2, argument is 6. Calculate that, and we get y is approximately equal to 7.75. So the point 0, 7.75 is our y-intercept. Determine the equations from the graphs below. So the blue graph is y equals log base 4 of x, and it's transformed to become the red graph. We want to figure out the equation of the red graph. The dots that they give us means this dot is transformed to become this dot. So this is 4, 1, and this is 1, 1. So 4, 1 is transformed to become 1, 1. Notice it's not a shift because our vertical asymptote for both graphs is the same. So it hasn't just been shifted to the left. We would have to have a horizontal stretch to go from an x value of 4 to an x value of 1. So what do we multiply to get from an x value of 4 to an x value of 1? We'd have to multiply by 1 over 4, which means that b equals 4. So our equation of the red graph would be y equals log base 4 of 4x. Same thing for the next one. We have y equals log base 4 of x again. It is transformed to become the red graph, and this point here, which was 4, 1 on the original, becomes this point here, which is 4, negative 3. Again, we can tell that we don't have a horizontal translation because our vertical asymptote is in the same place for both the blue graph and the red graph. We also don't have a horizontal stretch factor, so our b value is just 1 because our x values remain the same, 4 and 4. So it's the y value that's changing here. We go from 1 to negative 3. How do we get from 1 to negative 3? We would have to multiply by negative 3. So vertical stretch factor of 3. And since we would have to multiply by a negative, that would mean a reflection across the x-axis. So a equals negative 3, and then our equation is y equals negative 3 log base 4 of x. Scientists found that the relationship between the number f of flower species that a butterfly feeds on and the number b of butterflies observed can be modeled by the function f equals negative 2.641 plus 8.958 log b. Predicts the number of butterfly observations in a region with 25 flower species. So 25 flower species means that f equals 25. We can sub that into our equation. 25 equals negative 2.641 plus 8.958 log b. And then we want to solve for b. So let's isolate log b. We add 2.641. To get 27.641 equals 8.958 log b. Then we divide both sides by 8.958. $27.641 divide 8.958. That gives us 3.0856 ... equals log b. We want to solve for b, so we want to get rid of the log. Remember, there is no base here, so that implies base 10. Let's write this in exponential form. Then we get the base 10 to the power of the exponent 3.0856 dot 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 equals b. Then we can calculate this. 10 to the power of the last answer gives us 1,217.928 dot 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 equals b. Round to the nearest whole number. This would be b equals 1,218. Then it's a word problem, so we should write a sentence. So there would be approximately 1,218 butterfly observations in a region with 25 flower species. That brings us to the end of Chapter 8, Lesson 2.